time, I tried to cover all of stats because actually, if you understand how linear models work, you can pretty much do any set of statistical tests, ANOVA, ANCOVA, what have you. But I think today we should just stick with Ttest and ANOVAs because there's actually a lot to discuss just within those two topics within itself. And I also want to do a little bit of more simulation. Not to simulate a physical system this time, but actually to simulate what happens in the statistical test in order to figure out how to make your own confidence interval and what that actually means. And we're going to be using a technique called bootstrapping, which is kind of cool. And so I'm actually a diehard Coca-Cola fan, so I'm a little biased here. But we're going to be doing a caffeine data set. Actually, I found it from UFL. Actually, I don't know where this is from. But I went ahead and I combined. So they have their data set all in numbers, where these numbers and the column mean something. So I actually went to the description. I figured out what those are, and I turned it into a CSV file for us to really get into very easily. So if you go to my website, this is myname.com, go to our tutorials, you should see that there's a data set right here called cola.csv. And also I'll be copying and pasting into this R script so that we can share code back and forth once that loads up. So why don't we actually look at this data set really quick. I have it downloaded already. Right here, cola.csv, and I'm just gonna open it in like a text editor or something. So you'll see that this is a really interesting data set because things are pretty much nested. So for example, here, the first column we have product, and you'll see that there's Coke, and right next to it is brand, and you'll also see Coke. But if you keep going down, you'll see that now the product can be Diet Coke, and the brand is still Coke. This is just a way that you can separate data sets in different categories, depending on which thing you're trying to do. So if you just want to do Coke versus Pepsi versus Coke versus Diet Coke versus Pepsi versus Diet Coke, you can go back and forth between this data set really easily. You'll also see that there's a category here labeled sugar, and that'll be either sugar or diet. So that's just another way you can divide up the data set. And lastly, we have restaurant, and what these values are, these are basically replicate values. So if you imagine if we went into 10 Red Lobsters, I think these are 10. We went to 10 Red Lobsters, we went and got a normal Coke from them and measured how much caffeine content is in each one of those Cokes. So you'll see that a lot of these are repeated, so just keep in mind that our data set has replicates in it. And lastly, of course, like this is just a numerical, the amount of caffeine in that drink. All right, so let me find my RStudio. I actually don't know where it went. There it is. All right, and I'm gonna pop this out so we can see a little better. All right, so the first thing I'm gonna do, we need to load in the data set. So I'm gonna fly through this because this is something that we should already know. Set working directory. Mine should already be set, but just in case, I'm gonna go to my root. I'm gonna go to my Dropbox. It's in this folder, it's in that folder. Oop, we don't need that. So we'll do that. And also I will list.files just to see what files are in there. And I'm looking for cola.csv. So you should have downloaded this from our website and put it somewhere where you want it, either your downloads folder or a source folder if you have that. And so I'm just going to do read.csv and do cola.csv. And I'm going to save that into something called cola. All right. Just make this a little bigger. So now if I type in cola, then you can see there's my data set, Taco Bell, Wendy's, KFC, caffeine content, good stuff. So one little trick that I like to do actually is when you have like a large data set and you just want to visualize it really quickly, really fast, you can just do plot cola. And what that does is it gives you this giant matrix of plotting everything against everything. But it really quickly, you could see that if you wanted to look at the effect of restaurant and caffeine, then you would look at this plot. If you wanted to see sugar versus caffeine, then you could look over here. Some of these, like, for example, sugar and caffeine, there are only two things here, this top and this bottom thing, because it's either sugar or diet. So that's why these are very spread out. But this is a very easy way just to look at what your data set looks like very, very, very quickly. All right, so let's look at this data set a little bit. So again, I think you can see that caffeine is the only column that has numerical numbers, and everything else are characters. But the one thing that we need to check with before we start doing statistics are that R should understand that product, brand, sugar, and restaurant are not just characters, but they're factors. That gives it just a little bit more information to do the test. So what we can do, spread that back out, is look at the structure of COLA, STR. And you can see that here are some, so for every column is named here, and it tells you what type of data each column contains. So right off the bat, we can see product, brand, sugar, and restaurant are factors. And we can see some information about how many things are in there. So there are 4 levels in product because we have Coke, Diet Coke, Pepsi, Diet Pepsi, 4 things. And we can see that there are 11 restaurants. So that's one of the first things that you need to check in terms of your data set. Especially if you're going to be dealing with Ttest and ANOVAs and ANCOVAs where you have categorical things. If it weren't a factor, I'll just show you how to do that. So let's just pretend that product wasn't a factor. What you can do is do as.factor COLA product, right? So what you're doing is you're taking this column product in the COLA data set, and you're explicitly saying, I want this to be a factor. So the last little step is then you need to put this back into the data set. So then you can just do COLA $ product and do that arrow assigning thing. So again, this is like one of the things that I feel like you need to just like understand and get used to, is that you can call things, change them, and then replace them. This is a very common thing that you'll do in order to fix some of your data sets and clean them up. But we're taking the product column of the COLA data set, we're telling it we want it to be a factor, and then we're storing it back to where it originally was. So this won't do anything to our data set, but if this weren't a factor, that's a way that you can go back and add it in. All right, so the first sort of statistical test that we work with is one of the most basics is a student's Ttest. I found out, actually, I did a little research about like why it's called a student's Ttest, and I never knew this, but apparently the person who published this, their pseudonym or their nickname was Student. So it was just like, it has nothing to do with being a student at all. It's just like, that's what this person's name was, student's Ttest. But it's very simple to do that. And what we'd want to do, for example, if we look back at our plot data set, why we'd want to do a Ttest is, let's say that we wanted to know brand, right? Coke versus Pepsi, whichever ones these are, if the caffeine content is different between just Coke and Pepsi. So what we can do is, let's get that script back up here. What I like to do before I even run statistics is I like to see plots. I think they help me visualize and adjust my expectation of what things should be like. And so we've done scatter plots before, and that's just been adding an X and adding a Y. Nothing changes here except instead of X being a numerical a column, we can just make it one of these factor columns. So we can say COLA $, let's say brand, Coke versus Pepsi. And then Y is equal to COLA $ caffeine. We still want this to be a numeric. So if we run that, we get a very familiar plot. I believe that these bold lines are the median values. I have to look it up. So the boxes, I think, give you the interquartile distances, and then these are outliers. And we can look that up later. But this is just a very standard plot to see that in general, what it looks like, Coke has higher caffeine content than Pepsi on average. But we can't say anything about whether that difference is statistically significant or not until we actually run the stats. And from this stage, it's pretty easy. What we want to do, so the basic syntax for doing a linear model is going to be always y tilde x. And the way to think about this is y is your response variable. This tilde means is explained by, and x is everything that you want as an explanatory variable. So we can think about this y as being cola, $ caffeine, x being cola, $ brand, and we're almost there. The last thing we need to do is wrap this in a function called lm for linear model, and be very specific that we want this to be a linear model. And I'm just going to store this as brand model. Right. So I'll run this, and I've created something that's called brand model. And if we look at what we've actually created, we have estimates for these things. So basically, what this is saying is that. So let's start with this. We see that here the cola data set, we're looking at the brand, specifically the brand Pepsi. So on the other side is the intercept, and you always think of the intercept as the default state of things that you're testing. So if this one is Pepsi, the default state is Coke. So this gives us our mean estimate for Coke, which is 42.15, which corresponds to right around there. This is the median and this is a mean, so it's going to be a little bit off, but this gives us a mean value of Coke caffeine, and what this value gives us is the estimate for the difference between Coke and Pepsi. So if you wanted just to get the mean value of Pepsi, it would be 42.15 minus 4.843. It's still, these give us estimates, but they don't tell us whether or not this is a significant difference. What you can do is then just summary your model, and when you run that, you get this very somewhat complicated table. But again, if you'll, I think it was a good exercise to go through what those things meant. This is your estimate for Pepsi. This is your default. So by default, this is for Coke, and you can see that Coke has this estimate, and this is the p-value for that being significantly different from 0. And then you can see that this is the difference in the estimate of the mean value of Pepsi caffeine content, and it's significantly different from the default, which is Coke. So that's how you read these tables. The first one, the intercept, is always just your default value, and the significance is whether or not that's different from 0. And then everything else after that is the significant effect of this on the default value. The thing that you have to be aware of in R and any sort of computer programming thing, that you do is that the machines that we're using for now are very stupid. They're very dumb. They do exactly what we tell them to, with very little warning as to whether or not what we're doing is right or wrong. So this technically and mechanically is how you perform this t-test. But statistically, we've done something very, very wrong here, which is even though we get significant values, the problem with our data set is that if we just pull it back up really quickly, I mentioned before that we have replicates in here, right? So what the statistical algorithm is doing is treating each one of these as independent points. And that's okay if you're dealing within one treatment. For example, if you were just looking at Applebee's, we would have 10 statistical units at that point. But once we have these different restaurants, we no longer have the same number of statistical units as we do data points, because there's this nested thing where the Red Lobster caffeine content is much more related to each other than Applebee's. Just because there's that nested information that the statistical model isn't taking into account. And so what we've done is actually pseudo-replication, where we think we have more power than we actually have. So what we should have done, actually, if we wanted to do this test, about whether or not Coke or Pepsi has significantly different factors are that we should have condensed down Red Lobster. Instead of having them count for 10 different points, we should have had them count for 1 point. So we should have had 1 point for Red Lobster, 1 for Applebee's, 1 for Mickey D's, and so on and so forth. So there's an extra processing step that we need to do to condense all this stuff down. Luckily, there's a very easy way to do that. If you were to do this by hand without some sort of like pre-made function, what you'd have to do is take the average value for Red Lobster caffeine content, and then that'll be 1 point. Then take the average value for the next restaurant and the next restaurant and the next restaurant. And you know, you could do that just by doing like mean and then by doing subsets. But there's a way that if you need to do this to many different things and have it like subdivide out and subset into different things, there's another function in here called Aggregate, which is a really handy function. And actually, I am going to open up the help file so we can look at it. Ooh. Question mark. Oh. All right, so let's look at this really quickly. The aggregate, so first we need to feed it an X, which is the thing that we want the calculations to be performed on. In this case, our caffeine content. By, as very specifically says, it's a list of grouping elements. So in this case, we want to do put restaurant as one of the categories. So there's basically things that you want to subset by. The cool thing about using the aggregate function is that you could put in multiple things. So if you notice, we're actually testing Pepsi versus Coke, I believe, in our plots, in our statistical model. But you'll notice that there's also Diet Pepsi here and Pepsi. Like there's also nested structure within those. So we can also include those things in there, Coke versus Diet Coke, in order to get means into 4 categories instead of just those 2. And the last little thing that we need to do is input fun. You need to put some fun in here. So this is just the function that will be applied to the data sets once it's all subsetted. So in our case, it's the mean, right? We want a mean. But you could put anything in there. You could put your own custom function. You could put standard deviation. You could put median. Like it doesn't matter. It'll accept any function that will do the calculations. All right, so now that we've looked at the help file, I'll show you how to do the aggregate. So again, the X, what we want to do is the thing that we want to perform these multiple calculations on. So cola, $, caffeine. That's what we want. If you hit tab, it doesn't. So this is why I also wanted to show you the help file. This is one of the cases where it doesn't show you all of the arguments that can go into it. But we can see that we need a by. And again, it's very important to read closely the wording. It's a list of grouping elements. So we need to input a list into there. And this confuses a lot of people. We haven't really talked about lists. That's something that we'll do in the future. But you can just think of it as just a grouping of different things. They don't have to be the same. So like I said, we wanted to do Coke versus Pepsi. So that was brand, I believe. So we can do cola, $, brand, no, restaurant, right? Because we wanted to calculate across, get a single value across all restaurants. And I'm even going to throw in here cola, $, just make that huge, cola, $, product. So we can also get differences in Coke, Diet Coke, Pepsi, Diet Pepsi. Oh, and the last thing is we need fun. Make sure that's a capital N, capital FUN. And you know, usually if you were to put a mean function in there, you'd have a mean open close parentheses. This is one of the weird things where you can just not have those open and close parentheses. Actually, putting the open and close parentheses messes it up. So you just want to feed it the function name, and that's how it reads it in. And I'm just going to call this brand aggregate. All right. So I will run this. Nothing happened, which is good. But we've created something that's called brand aggregate. And when we look at what that actually looks like, you'll see now that everything is divided up into different restaurants, Coke, Diet Pepsi, and Pepsi. And then these values over here give us the mean values for every. So for example, in this first line, This 39.09 is the mean caffeine content for Coke at all Applebee's in our data set. And so that's an easy way that you can apply these functions and subsets across your entire data set. And you'll notice now that if we actually look at this data set, these are no longer replicates in the way that we thought of them, right? These, like, we can all consider these as independent tests. It's not like we've lost one level of nestedness in this, so that this makes us a little bit easier to do statistics. I'm going to do one more thing because I think this is annoying. It just adds in group 1, group 2, and X. I'd like to replace these with things that make sense. So if you actually do brand aggregate and you do the names function to it, you'll see that when I run that, it'll give me group 1, group 2, and X. So this is like another like weird cool trick in R, is that we just use this to punch something out. What we can do is instead flip it on its head and say that, well, I want to make my own vectors and then put it into that. So instead of having group 1 and group 2 and X, you could just concatenate together restaurant, product, and caffeine. I'll just make that big so everyone can see it. And I'll run that. And so again, we've made this list of 3 text things, and we're putting it into the names of brand aggregate. So now when we do brand aggregate, if you look at the top, you'll see that now we have our own custom names for those columns. In particular, there's this whole thing about IID, is that right? Your data needs to be independent and identically distributed. And the fact that our data was not independent completely violates all those statistical tests. And so we just do the same thing again. We can do an LM. And this time, instead of doing cola caffeine content, we want to do brand aggregate, $ caffeine, as explained by brand aggregate, $ product. And I'm even going to wrap this around a summary. So I can just skip a step, and we can see p-values there. So I kind of designed this in a tricky way, where I wanted to make a point here, which is what we actually did was not the same as the last thing. We basically extended our t-test instead of just having 2 factors into having multiple factors: Coke, Diet Pepsi, Pepsi. And just with that one little switch, we turned a t-test into an ANOVA. So mechanically, coding-wise, we didn't change anything at all. We just fed it a different set of factors. And I just wanted to show like how easy it is to that there's very little difference between a t-test and an ANOVA. It's all the same in terms of the coding, and also having this up, we can look at what this means in terms of the interpretation. So again, the hardest part of looking at these summary things from stats are determining what the intercept is. Because it doesn't give it to you right away. But we can see that this is divided up into products. So here's Pepsi, Diet Coke. This must be Coke, right? And it's saying that this is our estimate of Coke, and that it is significantly different from 0. That's fine. And let's put up the plot at the same time, because it might be easier to look at. So I'm just going to say plot X is going to be brand aggregate $ product, and Y is going to be brand aggregate $ caffeine, right? So we just plot it out and we can see. All right, so our stats are saying that Coke is significantly different from 0. I believe that. And what this next line is saying is it's comparing Diet Coke to Coke. And it's saying that Diet Coke has a mean value that it's about 8 higher, and that's a significant difference. So Diet Coke is significantly different from Coke, right? And these last 2 things, if we're looking at Diet Pepsi and Pepsi, they're not significant. And again, these are all comparing Diet Pepsi to Coke and Pepsi to Coke. That's how these summary tables work. And this might not be exactly what you want, because if you notice, these are all doing statistics comparing back to this intercept, which is the default of Coke. It doesn't tell you anything about whether or not Diet Coke and Diet Pepsi are significantly different. It doesn't tell you whether or not Pepsi and Diet Coke are significantly different. And that is one of the limitations of ANOVA. It doesn't do that multiple pairwise comparison. It just tells you whether or not, so at the very end, if you look at this p-value, we have a significant p-value, and all that means, all that you can interpret from that is that there's something that is significantly different in here. It doesn't tell you what. It just tells you that there's something different. And that, to me, is a signal that you need to do a post hoc test, something that, to pull out these pairwise relationships to see whether or not Diet Pepsi and Diet Coke are different, and whether Pepsi and Diet Coke are different, or whether Diet Pepsi and Pepsi are different. You might just say that, well, why don't you do just multiple t-tests, right? Like, if we can just subset our data set out and do Diet Coke versus Diet Pepsi and do a t-test and see if that's significant. And you could do that, but the problem is that the more t-tests that you do that way, you introduce more, I believe, type 2 error. I never memorize which one's type 1 and which one's type 2. But you basically compound your error by doing these multiple comparisons outside of a post hoc framework. But there have been tests that have been developed that allow you to do those multiple comparisons, but also minimize the amount of error you introduce. And that's one of the things that I'm going to show you how to do right now. There are two main ways. I'm a little biased just because the way that I learned was to do what's called a two-key test. The other way to do it is to do a Bonferroni correction. And what Bonferroni does is it does those multiple pairwise t-tests, but it adjusts your p-values to take into account the chance for extra error. Two-key does it a little different. I'll just show you how to do that really quickly, and then if people are interested in Bonferroni, I think I could look it up and do it really quickly. But it's actually, let me pull up the help file so we can look at it. The function that I use is capital T, two-key, and I believe it's capital HSD. And it's the two-key honest significant differences test, HSD. So the way that you do this, and this is, in my opinion, a little wonky, but it works, is you have your two-key HSD, and inside you have to put your model, but you have to modify it a bit. So in this case, our model is going to be a linear model. It's going to be brand aggregate, I believe that's what we called it. $ caffeine, as explained by brand aggregate $ product. And this on its own doesn't work. So if you just type that in, you'll see that it's not the right class. And all you have to do to fix that is you have to wrap your linear model function around an AOV, which is an analysis of variance. It's just another function. And that fixes it. So when you run this code, you see you get these. And again, this is pretty cool because you see the very specific differences: Diet Coke versus Coke, Diet Pepsi versus Coke, Pepsi versus Coke, on and on, and these adjusted p-values. So you can tell, without violating any assumptions, which of these categories are significantly different from each other. So what I want to do actually now, I believe these are confidence intervals. I've never actually looked at lower and upper, but I think they are. I actually want to talk about confidence intervals a little bit, because that's another way of looking at this and doing comparisons outside of a p-value framework, right? Instead of looking at whether or not these are significantly different and having a p-value for it, another way that we could look at this is if these are, I guess these are medians, but if we think about these as means, if these are our mean estimates for the caffeine content in each of these 4 categories, what is our confidence, like, can we bracket that to a certain extent and say that 95% of the time, if we were to repeat this test, our estimate for mean would fall in, like, somewhere in between? And if you could take 2 categories and look at their confidence intervals and check whether or not they overlap, you can say that 95% of the time, if we're confident that these 2 categories don't overlap, that they're different. So that's just another way to think about it. And there are ways to do it mathematically to figure out what your 95% confidence interval is, but I think it's also important to know how to do it more generally in a simulation sense, because there are some functions that you might want to do this for, maybe not mean, but maybe like if you go back to like last week's example, if you wanted a confidence interval on theta or like theta max or something, there's no analytical solution for that. That's something you'd have to simulate from your own data sets. And that's something that we can do here. So I'm just gonna do confidence interval. And I'm gonna make a function. I'm gonna say get CI. I'm gonna make it a function. What are the things that we need? We need to give it a data set. We need to tell it, so I'm going to make this very specifically for our product, our product set. So I'm going to say what product we want, and by default, I'm just going to give it Coke. I want to have number of simulations. By default, let's just give it 10,000. That sounds like a good number to go with. And the last thing that I think I want to put in is confidence level. And by default, you always hear of a 95% confidence interval. So I'm just going to put 0.95. I think that's good to start. I might have forgotten something, but we can, no problem. Some space there. We can fill in some of these parameters as we'd like. So basically, what I want this function to do in order to calculate the confidence interval is basically to calculate the mean caffeine content for Coke, given our data set, but not just calculate it from the values that were given. I want to resample with replacement from the values that we have in order to simulate, like, what if we could go back and do this experiment out in the wild over again? What could our mean values be, given that our data are representative of that, right? So the whole thing about frequentist statistics are that the whole idea of it is that when you calculate a p-value, it's like, what is the % chance that you could get the same results if you could repeat the same experiment multiple times? And so the other converse way of thinking about it is, well, if you can't realistically go out and do this 1,000,000 or 10,000 times, given our data set, we could simulate what, if those patterns hold true, we could simulate what could happen if we do that, if we went out and did that experiment multiple times using data that already exists. And so that's where the whole bootstrapping comes in. We basically take old data and use that as a guide or as a model that guides our understanding of getting these distributions. So the first thing that I want to do is subset the data set so that we only have the Coke products. So let's do temp subset, right? And I want the data set, and I want only the rows in which the data set product double equals product. So that was fast, but I can explain this one more time. So we're taking the data set. We want to subset the data set, and because we leave this blank over here, that means we want all columns. We only want to select certain rows. And the rows that we want to select are the rows in which the product is equal to the product that we put up here as a Coke. Everyone okay with that subset so far? All right. So what I want to do is I want to do a loop for I in 1 to n sims. Get that n sim. We'll do that. And what I want to do is I want to sample again with replacement from temp subset. So you can do that using the sample function. And these are the things that go into it. So X are what do you want to sample from? I want to sample from temp subset caffeine, right? And then how many do I want? I want as many as there are there. So you could do n row of temp subset. So let's just review what we're saying right here. This sample function allows you to pull things from a list of numbers. The list of numbers I'm pulling from are these numerical caffeine values, and the number of things I want to pull is equal to the number of things I have, right? So if we had replacement as false, this wouldn't do anything. It would sample every single value, but if we couldn't have replacement, you would just basically shuffle your caffeine content around, and if you take the mean of that, then order doesn't matter in the mean. By having this replacement, it's saying that I could sample from my 10 caffeine measures, I could sample the first one maybe like 3 or 4 times in that data set when I calculate the mean. So it gives us a little bit of noise in terms of calculating our mean. And so what I really want to do is do replacement equals true. Let's just call this temp sample, do that. Last little bit here is I want to take the mean of temp sample, and I want to put it into something that I can save. So simulated mean I. Right. So what I just did is I sampled some stuff, I took a mean, I want to save it somewhere. This does not yet exist, but I can fix that by going outside of the loop and just saying my simulated mean, and I'm just going to give it random values. I'm going to repeat 0 for n sim times. Right, so this just acts as a little thing that we can store values in. So before we go on, maybe this is a good time to check out what actually happens. So I'm going to return my simulated mean, just so I have a function. And let's just run this so we have it in our console ready to run. So I'm going to do get CI, and because we're just trying it out, I'm just going to make the number of simulations 3, right? Let's just have 3, see what that does. Oh, and we didn't put in a data set. So I am going to put in our aggregated, our data set is going to be, I can't spell, aggregated, what do we call it? Brand aggregate? Yeah, there we go. Just can't type today. All right. So those are some values. So what it did by default, it went into our aggregated data set. It looked at Coke. It sampled 3 times with some replacement, so we don't get the exact same values. But this is an idea of what would happen if we went out and repeated this experiment 3 times. This is one possible thing that could have happened. Right? These are a set of possible results that we could have gotten. Yes, yes. So actually one way that we could get the same numbers is we could just set our seed, and I'm just going to set it to 1, and that basically syncs up all of our random number generations to the same, so we can get the same results. So that's a good thing for reproducibility, for trying to teach someone how to do it. Like now, this would have been a good time to do that, but I didn't.
And what each of those numbers represent again?
So these numbers, right, so what we did is we went into our aggregate data set, and we went and looked at just the Coke values, the caffeine Coke values, and we sampled within those with replacement. So we'd have the same number of values of caffeine, but some of them could be missing, some of them could be replicated, and took the mean of that. And so this value is the mean of that. And then each value after that is if we went in again and we had different ones that are replicated, and then those are falling out just by chance.
Okay, so these are 3 separate random means of
Yes, yes. And again, these are all based off of our original data set. we're just sort of like, so the reason they call it bootstrapping is because you kind of get more out of your data set than what you started with. And so like, yeah. So we're almost there. What we'd like to do is not necessarily have these means, but we'd like to know, to get a 95% confidence interval, you basically would have these means, and you would say, you know, what are your 2.5% on either end? Like, what are the lowest and highest values? Not necessarily the lowest and highest values you get, because that would be like maybe like a weird 100% confidence interval, which sounds weird to me. But having that sort of a buffer allows you to say, this 95% confidence interval. So the way that you do that is you can sort your simulated mean so that you go from lowest to highest. And from this point, I'm just going to do simulated mean. I'm going to replace it, right? So I'll take it and make it a sorted version of itself. And all you need to do at this point is figure out how many things you need to cut off to get the lower and higher bracket. In this case, if we wanted to do two-tailed confidence interval, right, the lower 2.5 and the higher 2.5%, that's easy to do. You could just say that you want the value of simulated mean that is at 2.5% of the number of sims that you have. So you have nsim times be 1 minus the confidence interval. Oh, confidence. Confidence. No, that's how you spell confidence. Confidence level. Divide that by 2 for a two-tailed test, right? So in this specific case, I just made it general, but you can see that 1 minus the confidence interval here would be 5%. Divided by 2 is at 2.5%. So 2.5% times the number of sims you have could possibly give you a non-integer. So the last thing you need to do is just round it. And so that was a lot of shortcutting math to get this. But again, what you're doing is, because you're sorting everything from lowest to highest, and you want to pull out that value that's 2.5% away from the lowest value that you have, this is the way that you can pull it. Right. So this is to get the lower confidence interval. To get the higher confidence interval, it's practically the same thing, except you don't need to do -1, right? So then this will just be 95% divided by 2 to get it on the higher end. And to actually get this out, I'm going to return both of them as a concatenated thing. So I'm going to concatenate this. Had to put a comma there to do that, and do this. Let's see if this runs. If this runs, I will put this up for everyone to see. I just want to check it. So now I'm just going to get rid of number of sims, go to default. That's not bad. All right. So I will copy this, put this on here for everyone to look at if you want to look at it on your screen. And just put that up there for people. Now that we have this function, I'll show really quickly that, so this, we had our product as Coke. We could do it for Diet Coke. We could do it for Pepsi. We can do it for Diet Pepsi. Just really easily, because we have this function set up the way that we did. And now you can sort of see, these are, you can think about these as lower and upper bounds with 95% confidence of where that mean value of these are. And so you could see that, for example, Coke versus Pepsi, those confidence intervals overlap. So it's very difficult to say that those are significantly different. You could see that Coke and Diet Pepsi also overlap, as does Diet Pepsi and Pepsi. But you can see the confidence interval for Diet Coke is way outside. And in general, this is just another way to show that, non-overlapping confidence intervals are a way to show that things are different. And again, getting away from the whole reliance upon p-values is kind of cool. And so in our example, when we did it, again, I just want to say that we hard-coded mean into here, right? Like, this is just the mean confidence, the confidence interval of the mean, but you could just as easily replace this with any function that you want and get a confidence interval that way. Our strategy in this case to deal with pseudo-replication was to basically crush everything down into a single data point where we could. That's really unfortunate because, we had a lot of data points, but, they only count as one degree of freedom, basically. The other way that we could have attacked this, and where we're going to go with our sort of like step through statistics, is learn how to deal, instead of treating our spread of replicates as one point, to treat those spread of replicates as a distribution, right? And that way we can get into what are called mixed models, where we don't necessarily have to crush and condense everything down into a single data point, but use the distribution within those sets to tell us something, to basically use the data instead of having to crush it down. So that's maybe where we might do our next thing. We didn't do any continuous by continuous sort of models, but those are pretty much the same. But definitely either next one or the one after that, we're going to touch on some mixed models.